So the relationship between pKa, pH is going to be relating to Ka, which is the acid dissociation constant. Dissociation constant, where the higher the constant, the more willing an acid is able to release a proton, right? So if we have this acid here, HA, and this is the proton of the acid right here. If this is a strong acid, it will have a high Ka constant because it's more willing to release or donate a proton, and a proton is a hydrogen atom right there. That's different than a hydride. H plus with a positive charge is a proton. H minus with a negative charge is a hydride ion, right? And this would create the conjugate base, which is the negative charged version of the acid, right? So let's say we have strong acid versus a weak acid. Right? Strong acid is going to have a high Ka value. Weak acid is going to have a low Ka value. When we convert this Ka into pKa, it's like a logarithmic scale. They're going to be inversely related. So a high Ka is going to represent a low pKa value. Right? So the more acidic a molecule is, the lower pKa it will have. This is probably going to be the more important, more common value we look at. So the weaker the acid is, the higher the pKa is. So a way to remember this is related back to pH. Right? In low pH, that's acidic conditions. In high pH, that's more basic conditions. So pH and pKa are directly proportional. Right? If we have a strong acid, it's going to have a low pKa. Like if the environment is acidic, then the environment is going to have a low pH. Right? So if we had a strong acid right here, the conjugate base is going to be more stable. Right? Meaning that this conjugate base right here can hold onto this negative charge better. Like it's going to be stable with that negative charge. And there's different factors that allow for this negative charge to be stable, like electronegativity. If the atom is more electronegative, then that atom is better able to hold that negative charge. Another important factor is resonance. Right? Like if that molecule is able to do a resonance, allowing for the negative charge to move around or be delocalized, think of it as breathing room. The more resonance a molecule has, the more space it has for the charge to move around, to breathe, which makes it more stable, right? So if it's more stable, do you guys think it will be more or less reactive if it's at peace? Like, will it be more or less reactive?
Less.
Yeah, less reactive because it's happy, it's at peace, so it's gonna not want to react with anything, right? It's not angry, so it's gonna be less reactive. So because it's less reactive, this is going to be a weak conjugate base. So a weak conjugate base is going to come from a strong acid. So it's going to be the other way. If we have a weak acid, it's going to create a less stable conjugate base, meaning that this conjugate base is angry. It doesn't like to have this negative charge, right? When we have a weak acid and that weak acid tries to release a hydrogen, this conjugate base here is angry. It doesn't want to have that negative charge. So that's why we call it less stable. And if it's less stable, it's going to be more reactive. It wants to react with something to go back to its original form, its more stable form. So if that's the case, then this is a strong conjugate base, right? It's a strong conjugate base because it's angry. It wants to pick up a proton and go back to its original form, the acidic form. Right? Strong conjugate base. Okay. Okay. So let's say, for example, I have this as my acid versus, let's say, this as my acid. And I put some kind of base to deprotonate this acid, right? Deprotonate meaning that we're going to take away a proton from this structure here. When we do that, we're going to form these conjugate bases here, OH minus and NH2 minus. So this is the conjugate base of these acids right here. And then the base is just going to pick up a proton, so both of them are going to have a protonated base. Okay. Base, H plus. And these are the conjugate acids of the base. But we're not worried about the conjugate acids. We're going to determine which acid is stronger. So to determine which acid is stronger, or which one will have a lower pKa, right, meaning the stronger acid, we look at the conjugate base stability. Which negative charge do you guys think that molecule is more stable? The negative charge on the oxygen or the negative charge on the nitrogen? Which is more stable?
The oxygen.
Yes. Because of what factor?
Because of electronegativity?
Yeah, because of electronegativity, right? The negative charge was supposed to be on the oxygen because it is more electronegative than the nitrogen is, making that negative charge more stable and this negative charge less stable. Right? Meaning that this is a weak conjugate base because it's so stable, it's at peace, it's not as reactive. So it's a weak conjugate base. Whereas this is less stable, it's more angry, it's going to be a strong conjugate base. Right? It's reactive. Meaning that this right here is a stronger acid. Meaning that it will have a lower pKa. And this right here is a weaker acid, meaning that it will have a higher pKa. Right. Okay, so now let's go over pKa and pH. Like at a certain pH, what charge would this group have based on this pKa? Right. Okay. Yeah.
Is there a question?
Yeah. Any questions? See one question.
So, if we have a weak acid,
Yes.
it can buffer well against base being put into it.
Right, so the buffer thing is going to talk about like physiological pH. So that's talking about the carbonate bicarbonate buffer system. Let's go over that. Let's go over that right now.
Okay.
Yeah. Okay. So the carbonate bicarbonate buffer system is what the body uses in order to maintain an optimal pH, right? A physiological pH of around 7.2 to 7.4, which is around neutral pH, right? As our cells do cellular respiration and we breathe or do exercise, CO2 is being formed as a result of cellular respiration. This CO2 in our body is what we breathe out, or if it mixes in the blood, it will react with the water in the blood. Right? This water is coming from the blood right here. CO2 reacting with water is going to create carbonic acid. So that's the first reaction that happens. As we increase carbon dioxide, it's going to favor this side of the reaction, right? Le Chatelier's principle is trying to maintain homeostasis. If we introduce a stress to the system is trying to do what it can to balance it out. If we increase the carbon dioxide on the left side of the reaction, we want to use that extra reactant and convert it into a product, right? To balance it out, right? You can think of it as like we have more a source of carbon dioxide, which allows it more things to like more carbon dioxide to convert it to carbonic acid right here, right? This carbonic acid right here is going to be dissociated into a proton and carbonate. Right. Where this carbonate here is the conjugate base of this carbonic acid. And this is a relatively weak base, weak conjugate base. But as we breathe in more, as we use cellular respiration and we produce carbon dioxide and we exhale it, let's say this increases, right? As this increases, the equilibrium arrow is going to favor the product side, creating more carbonic acid. And as more carbonic acid is being increased, this is the reactant of this reaction here, right? So we could separate this into two different reactions. The first reaction is going to be this. The second reaction is going to be this, right? The product of the first reaction is going to be the reactant of the second reaction, right? Because this is the reactant, this is the product of the first reaction. We're going to use that product of the first reaction as the reactant for the second reaction here, right? So as this carbonic acid is being increased right here, we do the same Le Chatelier's principle. We're going to shift the reaction more towards the product, right? In order to maintain homeostasis. If we are increasing the reactant, we're going to make more product. So if we are increasing proton source in the body, would that increase or decrease the pH of the body?
Decrease.
Decrease the pH of the body, right? Because it's becoming more acidic. Right, more acidic. And if it becomes more acidic, it's gonna go lower than 7.2 to 7.4, which is the optimal pH we want in our body, right? So our body would counteract this effect by having this carbonate react with the proton, right? So as this H plus here is being increased, this H plus here is going to react with this carbonate and consume this carbonate, right? This H plus here increasing in the body is what we call acidosis. And even though this is a weak base right here, we consider this as a strong acid, right? And strong acids would be able to react with any kind of base, even if it's weak, right? But if we had a weak acid and a weak base, those would not react with each other. But think of this as a strong acid. Let me write that down. Strong acid. Right. This right here.
And in this example, where are we getting the increase of hydrogen atoms?
Yeah, in this example, we're getting an increase of hydrogen ions or protons from the carbonic acid, right?
So it's just playing with itself.
Yeah.
God.
Easy,
Oh,
easy.
Yeah, it's going back and forth because this is the equilibrium right here. Right?
Okay.
So it's going back and forth like that. That's why we call it a buffer system.
Okay.
To avoid going too down to the pH or too above the pH. This one here prevents going like too below the pH, right? Too acidic. If let's say, for example,
And then the carbonic acid stops it from getting too basic.
Yes, it stops us from becoming too basic because let's say we don't have as much protons as we want it to be, right? That would increase the pH to like, let's say above 7.4. That's not ideal.
Right.
If that was the case, like if the proton is low in the body, meaning that we have a high pH, we're going to counteract this by producing more carbon dioxide in our body. We're going to do more cellular respiration. And when we do more cellular respiration, we're going to create more carbonic acid, which is able to dissociate into more proton source, increasing the proton concentration and like decreasing the pH to counteract that. Right. So the body is going to do what it can to maintain this optimal physiological pH.
So where does pressure play a part in this? Because we kept talking about the pressurized can.
The pressurized can, let's see.
Because when you pop a Coke, you know, it fizzes
Oh,
due
that's
to.
what you're saying. The
Oh,
CO2.
the CO2,
Yeah.
the gas,
So he was
Yes.
pretty much saying that the CO2 was like being released from the soda.
Yeah, because soda, like, is it carbonated? Right? If it's more carbonated, it wants to maintain like homeostasis, so it's gonna go shift towards the left side of this whole reaction. And there's a lot of carbon dioxide in the can, but the can is trapped,
Pressurized, so the carbon
Pressurized.
dioxide can't get out.
can get out, right? And as we release it, like add like more volume, that's when it yeah, that's why we get that pressurized can.
We get the pressurized can because we force CO2 into it, and then it reacts when O2 is introduced.
Sounds right.
O2.
Maybe.
Oh, oxygen?
Yeah.
O2. I've learned about that yet, so I'm not
Okay.
too sure.
No, that's cool. I appreciate this as it is.
Yeah. So this is the carbonate bicarbonate buffer system. Let's go over pH and pKa and how to determine the charge at a certain pH. Like, is it negatively charged or positively charged?
Yeah.
Okay.
One last thing.
Yeah.
The bicarbonate, that is a weak base, correct?
Bicarbonate is a weak base. Correct.
Thank you.
And the reason why is because if we draw the structure of bicarbonate out, HCO3. Oh, this is not it. This is yeah. No. This is supposed to be HCO3, like this. Right. This negative charge right here on the oxygen is able to do resonance with the carbonyl, the carbon double bond oxygen, right? Because this double bond right here is right next to the negative charge. Whenever you see a double bond next to a negative charge, think of resonance. Or more breathing room for the negative charge to move around, more playing room for the negative charge to move around, making it more stable. So if you have resonance, the molecule is going to be more stable because it's delocalized, meaning that it's not stuck, it's not localized. Right? It can move around freely. And if it can move around freely, it's happy, more stable. If that's the case, would this be more or less reactive if it's more stable?
Less.
Yes, less reactive. It's at peace. It doesn't want to react with anything. And because it's at peace, it's less reactive, we consider this a weak base. Because of resonance.
Cool.
Right. Okay.
I feel like you insult the base when you call it weak.
Weak?
Well, it's definitely like a mind twister because it's actually strong in resistance.
Yeah.
Yeah,
But
strongly
we're
resist
calling it
resistance.
weak.
In different terms.
Yeah, right.
Right. A strong base would be like hydroxide ion, like NaOH, where the negative charge on this oxygen here cannot do resonance. Right?
Oh, yeah.
There's no double bond next to this oxygen.
Right.
No resonance, so it's localized, it's stuck there, it's very angry,
Yeah.
very reactive, so it's a strong base. Have you guys printed out the notes for the exam tomorrow yet? Like the
Oh, we've got a few, but I don't know about them.
Sure. Okay. So the general structure of an amino acid is gonna look like this. So let's say this is at physiological pH, like optimal body pH. There's three components of the amino acid that will always stay the same for all amino acids. Right? The amino group and the acid group. That's why we call this an amino acid. Because
Oh, the amino and carboxyl.
yes, amino and carboxylic acid. That's why you combine together, amino acid. Right. This carbon right here is the alpha carbon. Right, and it's called the alpha carbon because it's the first carbon away from the carbonyl carbon, carboxylic acid carbon. I'm going to draw in a structure that's not an amino acid, where let's say we have a carboxylic acid like this, and we have a long chain like this. This is the carbonyl carbon or the carboxylic acid carbon. The first carbon away from that carbonyl carbon is the alpha carbon. The second carbon is the beta carbon. And then the gamma carbon, delta, epsilon, and so on and so forth, right? So we're gonna see these Greek letters when he mentions beta carbon, gamma carbon, delta carbon, epsilon carbon. This is what he means by that, right? The distance from the carbonyl carbon. So when he says alpha carbon, it's the first carbon away from the carbonyl carbon, right? This hydrogen here is always going to be there as well for the alpha carbon. But this R group right here is what we call the side chain. And this side chain here is what makes amino acids different. Where these side chains can have different properties, and that's like what you put in the notes, like which ones are polar, non-polar, acidic, basic, positively charged, negatively charged, ionizable. Okay. So at physiological pH, the amino group is protonated, right? The term protonated means that this amino group here has a proton, right? It accepted a proton.
Question.
And this carboxylic acid here is deprotonated, right? Because usually carboxylic acid has a carbonyl group and an OH group right here. But when it gets deprotonated, its hydrogen gets released, right? And when it gets released, this oxygen atom here gains a negative charge. Whenever something gets deprotonated, it always loses a charge. It always loses a charge, right? Okay. So there's two scenarios where you can see this question. If I have, let's say, this amino acid right here, and let's say everything is protonated. And let's say the R group is this right here. This is valine, right? I'm going to introduce something called a pH elevator. Right, pH elevator. Yeah, see you, man.
Bye.
Yeah, bye. The pKa of the carboxylic acid is usually going to be around 2, but on the exam, he will give us the exact value for the pKa. So let's say this is pKa of 2.1. And the pKa for the amino group is going to be around 10. So the pKa of this group is, let's say, 10.4. Right. pKa is going to talk about the intrinsic property or characteristic of the group that we're talking about. So the pKa of the carboxylic acid here is talking about how willing is this carboxylic acid to release its hydrogen. If it has a lower pKa, will this carboxylic acid be more or less willing to donate its proton? If it has a lower pKa.
More
Would it-
willing.
More willing, right? Because lower pKa means stronger acid. Stronger acid meaning that it's going to be more willing to release a proton. Higher pKa meaning that it's less acidic, so it's less. This amino group is less willing to release its proton. The pH is going to talk about the environment solution, the surrounding solution. So if I have a pH of 0, meaning that the surrounding solution is very acidic. There's a lot of proton sources around, right? That means that this carboxylic acid here cannot do its job as an acid, right? Because the pKa here is higher than the environment. The environment is more acidic than this carboxylic acid group, so the environment is going to protonate that group. So at a pH of 0, everything gets protonated. Right? Like that. But as we rise up the pH elevator, let's say at a pH of 6, what group is going to get deprotonated at a pH of 6?
The carboxylic acid group.
Yes, the carboxylic acid group, because now the carboxylic acid group is more acidic than the environment, right? The pH, think of it as the environment. Because the carboxylic acid is more acidic than the environment, this carboxylic acid is going to protonate the environment. You can think of it like that, right? Now we can do its job as an acid and protonate the environment to give us this structure here. Right? And whenever we deprotonate something, we take away a charge, -1 charge. This was overall neutral, 0, 0 minus 1, -1 charge. Right? Let's move up the pH elevator again to, let's say, pH of 12. Now at a pH of 12, all of the groups here in the amino acid are more acidic than the environment, right? The environment is extremely basic now. And because it's extremely basic, it's going to deprotonate these amino acid groups. So when we deprotonate it, this amino group had a +1 charge. +1 minus 1 is 0. So the overall charge of this amino group is going to be neutral when we deprotonate this amino group. Right? When we take away a proton, it becomes NH2 neutral. Right? But the carboxylic acid started off as neutral, a charge of 0. 0 minus 1 is going to be -1. So if we were to see the net charges of these amino acids, the net charge of the bottom one here is going to have a +1 charge. Net charge of the middle one is going to have a net charge of 0 because +1 minus 1 is going to be 0. They're going to cancel each other out. This will have a net charge of -1. And there's a special name for this amino acid here.
That's the isoelectric form, right?
Yes, this is at where the pi is going to be at, like where the pi is going to be at. It's going to be around 6. It's not exactly pH 6, but it's going to be somewhere near here, right? And we experimentally determined that pi. There's some calculation cycle behind that, but the pi is when the net charge is 0. But do you know the specific ion name of this? This is a weird name. Rhymes with Twitter.
Oh, it's Zwitter ion.
Zwitter ion. Right. A Zwitter ion is what we form at the pi, the isoelectric point. So this is going to be near the pi. Isoelectric point, where we have a net charge of 0. The isoelectric point is when we have a net charge of 0 in the solution, creating the Zwitter ion. So that was the scenario when the R group was not ionizable, right? It had no proton, no acidic proton to deprotonate. It gets harder when the side group can get deprotonated, where we have 3 pKa's. on the amino acids. But we will always have two pKa's for all amino acids. One pKa for the amino group, another pKa for the carboxylic acid group. Some amino acids will have three pKa's, where the third pKa is going to be from the from the side chain, the R group. So for example, we can have this amino acid here with this R group. Yeah, this is either aspartic acid or glutamic acid, not too sure, but that will be on the for the notes. This will have three pKa values, one for the amino group, one for the carboxyl group, and one for the R group, right there, because we have an acidic amino acid here. Let's say the pKa for the amino group is 10.2, the pKa for the carboxylic acid is 2.3, and then the pKa for the R group is 3.1. Now, if we look at the pH elevator, oh, this is gonna be interesting. I'm gonna give you guys 1, 2, 3, 4 different pKa's, and I want you guys to draw out the structure
Alright,
of what it
alright.
would look like. Right. At a pH of 0, at a pH of 3, at a pH of 6, and a pH of 14. Right. The different floors of the elevator. And not only that, I want you guys to also determine the net charge. Okay.
Have to give a body a minute here.
Yeah. Okay, I'm gonna see if the restroom's open now.
Do it. How you doing? We'll see what I get. Yeah, right? I feel that.
this problem here is with an acidic amino acid. We'll also do one with a basic amino acid because it's going to be a little bit different. And then after that, I think the amino acids like properties, like that's more of a note thing, right? Like the which one's polar, which one's non-polar.
Yeah,
Right. This one's more conceptual, like how to like determine the charge. of
Which
groups.
is what I've been struggling with, is
Right.
like conceptually.
Conceptually, yeah. Have you guys had the chance to figure out this pH elevator?
I think so. But you mean,
That's right. If you guys make a
I think
mistake, don't
so.
worry, because it's best if you guys make it now, so you guys like avoid it on the exam. you know?
yeah,
Like,
exactly.
learn from the
I'm
mistake.
so grateful that you're willing to spend this time right now.
Yeah, no problem. Like I'm having fun tutoring.
Great.
Yeah.
Here for your tutoring, because the other one was not helpful.
Okay, sure.
Let's be real.
Are you Nikki?
Yes.
Yeah.
Yeah. Brian, right?
Yes, Brian. Yeah, I remember you saying your name Google Meets. Yeah. Right. Yeah.
Okay, so for pH of 0,
Yes. You can come up and try like drawing on the board too if you're like okay with being on camera. Or it's like-
You should edit.
Okay.
Just so you know.
Yeah. I'll just draw it out. Just explain to me what it should look like.
I got a positive 1 charge and essentially no change to the molecular structure as it is.
Right. So this is a original. G plus 1. Right. That's good.
Neat. What's
What?
the next one? Or sorry.
Yeah.
I got +2, I don't know.
Plus 2. Yep. So at a pH of 3,
But
Let's
all
see.
can- I
oh,
don't know how I got 2.
right. So can I see what you tried?
I don't know what I did.
right. Plus 2. Oh, for the original one.
Mhm.
Yeah. So at a pH of 0, everything is gonna get protonated, right? Because the environment is more acidic than the groups.
Mhm.
This carboxylic acid right here is already protonated. And when this carboxylic acid is protonated, it's going to be neutral. So when you see a carboxylic acid, which is a carbonyl next to an OH group, when it's protonated, it won't have a positive charge. It's going to be neutral, right?
Okay.
Yeah, just like how I drew up there. Once that's the protonated form of the carboxylic acid. It has no positive charge. It's going to be neutral, right?
Okay.
Yeah, this is good. Like you're saying like the things now, you know.
Okay.
Yeah, and because it's neutral, the net charge is gonna be +1 from that amino group right
Yeah,
there.
right here.
Right.
Cool.
Mm-hmm. Right. Okay. So,
For pH of 3, I
Mhm.
got a net charge of 0.
yes, and net charge of 0. That's correct. And which group would get deprotonated? The amino group, carboxyl group, or R group?
The carboxyl group.
Yes, carboxyl group. That's right. Right, because the carboxyl group is more acidic than the environment, which makes it able to do its job as an acid and release its hydrogen, becoming a -1 charge, negative charge. 0 minus 1, negative charge, like that. Okay. pH of 6.
Do you have a guess for that, Nee?
Then I got the whole concept wrong.
Okay. I got a -1
Yes.
charge.
Negative
And
1.
Both the carboxyl group and now the R group have been deprotonated.
Right, because now both the carboxyl group and R group are acidic enough, more acidic than the environment, to get deprotonated as an acid. Right. And notice the trend here, as we're moving up the pH elevator, the overall net charge is -1, -1, -1 every single time. Right, because every time we deprotonate the whole structure, we always -1 charge. Right. At the original structure, it had +1. When we deprotonated it one time, like as we rise up the pH, it went to 0.
Yeah.
As we increase the pH by adding like a base or something, -1. So if we follow the trend, what should we predict the net charge to be here? -2. Yep. And we can confirm that by saying what groups get deprotonated here. At a pH of 14, all of the groups will get deprotonated because all of the groups are now more acidic than the environment. Right? This group here, like it seems weird saying that this group is acidic, but relative to the environment, this group is more acidic than the environment, right? Because 10.2 is lower than 14. Lower number means more acidic. So this can do its job as an acid and release a proton. And whenever it releases a proton or something gets deprotonated, we minus one charge. So when this gets deprotonated, what charge should the amino group have? Right.
It should be neutral.
Yeah, it should be neutral, right? So that's the other commonly like overlooked thing as well, because we are used to seeing something getting a negative charge after it gets deprotonated, but not for the amino group.
Mm-hmm.
When the amino group gets deprotonated, it becomes a neutral charge.
Because it was already positive.
Yeah, because it starts off as a positive charge. Whereas the carboxylic acid, its protonated form is neutral. And when we deprotonate that neutral thing, it becomes like minus charge right here. Right. Uh-huh.
Cool.
Yeah, and which one is the PI? Where would the PI be at? Close to? At what pH would the PI?
pH of 3.
Yes, so
Because the charge is neutral.
Right. The PI would be somewhere around here, where the net charge is neutral, creating a Zwitter ion. Yeah. Okay. So that was acidic amino acid, and a basic amino acid could be a little bit trickier, but it's gonna be following the same concept. 1, 2, 3. 1, 2, 3. Right. Is it? Yeah, I think so. Arginine. Okay. See, the pKa for the R group is going to be 13.1. pKa for the carboxylic acid is going to be 2.8. The pKa for the amino group is going to be 9.2. Okay. So instead of doing the whole pH elevator thing, I'm gonna ask this question in the form of what it would be like in the exam.
All right.
Yeah.
Let's do it.
And I'm gonna give you guys 3 different ones. Let's see.
Hola, Marcos.
Buenas noches.
Buenas noches. ¿Cómo estás?
Hi.
Bien, bien.
Maestro.
No, un estudiante, pero enseñándonos, por supuesto. Maestro de esto, sí.
Maestro.
Sí.
Okay, good night.
Night.
Oh, I see what you're doing. Hello.
I'm so sorry. I would have came and moved my stuff earlier.
Hey, Alex.
Hey, Bryant. Oh, my bad. I want the video.
No, it's okay. Okay. Yeah, it looks like it's a little bit inverted. But the first question is asking for what charge will the amino group have at a pH of 6. The second question is asking for what charge will the carboxyl group or carboxylic acid group have at a pH of 8. And the last question is asking for what charge will the side chain, this arginine side chain, have at a pH of 14.
Also, if you guys go in the edit, you can just flip the video. Just press edit and you can flip the video.
Yes, that too, that too. Oh wait, can I invert it like after like it's
Oh, yeah,
done
you
recording?
can, before you even send it.
Yeah, yeah.
He's so smart.
No, I got the idea from you. The second one. So if we look at the pH, think of that as the environment, the surrounding solution.
Right.
At a pH of 8, then I look at which group would get deprotonated, right? Which group is more acidic than the environment? Or which group has a lower number than the environment, lower number than 8? Yes, this one. So because this group has a lower number than 8, that group is going to get deprotonated. It's going to have a -1 charge, right? Originally, it's a 0 charge. The 0 minus 1 is negative charge.
Bye, guys.
Yeah.
Bye.
See you, Alex.
Bye. Happy studying.
Thank you. So this group here is going to act as an acid in this pH because it's a lower number than that pH. When it acts as an acid and gets deprotonated, we take away a charge, right? Overall, it's neutral. 0 minus 1 and negative charge, right?
Yeah.
Oh shoot, yeah, and then that wasn't like what the question was asking for, but it is. But then I didn't read the question, right? But luckily it asked for the carboxyl group.
Yeah.
So this is the carboxyl group right here. So the answer would be negative charge, -1 charge, right? But this could be a little bit more tricky if it asks for, let's say, the R group, the side chain, have a pH of 8. So if you look at the side chain here, we notice that the pKa is higher than the pH, right? So would that make it the base or the acid if it's higher than the environment?
I know it won't change,
Yeah.
right?
Yeah, it wouldn't change, right? Because it wouldn't get deprotonated. It can't act as an acid. It can't do its job as an acid because it's higher than the environment. Or you can think of it as like the environment is protonating the group, and this is its protonated form. So if it asks for the R group or the side chain, the answer would be positive charge, right? So we have to read the question carefully to see what it's asking for. But this is asking for the carboxyl group, which is going to be -1. Okay, let's try this one.
What charge will the side chain have? This is the side chain.
Then we see if it can do its job as an acid and -1 charge.
So it will depro.
Yes, it will be able to deprotonate because its pKa is lower than the pH. So it can do its job as an acid and donate or release a proton. And whenever we donate or release a proton, what happens to the charge of that group? Does it remain the same, -1 or +1? minus 1, right? So right now, originally, it's plus 1. Plus 1 minus 1 is 0. So the answer would be 0. Yes, that's the answer, right? A lot of people would have had this wrong because whenever people think of deprotonating something,
Oh, it becomes negative.
a negative charge, right? But that's not the case for this side chain right here. When this gets deprotonated, it becomes 0, neutral.
Okay.
Because originally, its protonated form is positive charge, right? Which, that concept, whenever we deprotonate something, minus 1 charge is always going to be there, right? That's still there. But in this starting protonated form right here, plus 1 minus 1, 0, right? But most people think about the carboxylic acid,
Yeah.
the neutral form, starting form.
Wow, that's so many little rules that you have to
Yeah.
remember.
I know, like a lot of like small, specific, hyper-specific details, right?
Yeah.
Yeah.
Because then this one becomes neutral.
When it gets deprotonated,
Yeah.
right?
And this one is neutral, so it becomes deprotonated negative.
Right.
And this one
Uh-huh.
becomes deprotonated, but it's plus, minus, so it becomes 0.
Right. And then when we go over titration curves, right, like next week or something, we're gonna talk about polyatomic acids, like H3PO4. Right now, its overall charge is neutral. When we deprotonate it, take away hydrogen, what charge would this have? Neutral, minus 1?
Minus 1.
Minus charge, right? And this is the proton that you got released. Now, this molecule here has 2 more protons to donate, 2 more protons to release. So if we deprotonate it again, we're gonna have this HPO4. What charge would this HPO4 have?
Neutral.
-2.
Negative?
Right, because when we deprotonate it, we always minus 1, right? But its form right now, right here, before we deprotonate it, is minus 1. So minus 1 is minus 2,
Oh.
-2. But it still has 1 more proton to deprotonate. So let's try it again. If we deprotonate that and have PO4 minus, what would that have? What charge would that have? When we deprotonate this.
-3.
Right, because minus 2, minus 1, -3. Right, -2 minus 1 is -3.
Oh.
You're taking away a
Oh.
positive
Yeah.
charge.
Yeah, you're always taking away a positive charge, right, right.
So
And this is like a phosphate ion or something, yeah, right.
conceptually overall,
Uh-huh.
if the pKa is less than pH,
Mhm.
you're going to deprotonate
Right, it could do its job as an acid and deprotonate,
and you're gonna minus 1 charge.
minus 1 charge.
If the pKa is more than the pH,
Yes,
you're going to protonate it
yes,
and you're gonna add a charge.
yes. The environment solution will protonate the group,
Or not always.
and adding a charge, it depends on what the group is. Like, for example, the carboxylic acid protonated form is neutral,
Right.
but the amino group is, like the protonated form of the amino group is positively charged. So it depends on what the group is. And then this goes like deeper into like the Gen Chem, like how to calculate formal charges of
Yeah.
things.
We don't need
So
to.
that's more tricky. yeah. That's gonna be like breaking it down even more deeper.
But I guess maybe
Yeah.
if the pKa is more than the pH, like let's say instead of carboxyl group, you said what is the charge of the side chain at the pH of 8? It's not necessarily that the side chain was protonated, it just wasn't affected by the pH.
Yes, at pH of 8, if you are looking at the side chain, then the side chain would stay protonated.
Yes,
Yeah.
it's not that it was protonated by
Uh,
anything, it's just that it keeps its
protonated form.
form that it's already in
Right.
at that pH.
Well, actually, it does get protonated by something, which is
Okay.
the surrounding solution. Right? Because whenever we talk about pH here, we're describing the environment that the amino acid is in.
Okay.
The pH is, let's talk about the environment. So at a pH of 8, there's a lot of H pluses around, which is protonating this R group right here.
Okay.
Right? So the environment is protonating this amino group right here.
I see.
Yeah.
It's
Right.
when that is willing to give up its hydrogen.
hmm
Got it.
Right. That's when the environment
Because
becomes,
it needs to be more basic.
Right.
Okay.
because when the environment loses H plus ions, it becomes more pH. Its pH increases, right?
Okay.
So that means that this group wants to like relieve that stress. It wants to like maintain homeostasis and act as an acid and donate a proton to the environment because the environment is losing protons. Right. This is an intrinsic characteristic property of the group. It doesn't change. The pH, we can change that, right? By either adding acid, decreasing the pH, or adding a base, increasing the pH. And that would therefore affect the groups, like if they're protonated or deprotonated, right? And the charges as well, right? So did you get the answers for the questions here?
I got 0 for 14 for the side chain, -1 for pH of 8 for the carboxyl group, and then +1 for the amino group at a pH of 6.
Yeah, that's right. Yeah, right. Because at pH of 6, the amino group is going to get protonated because it cannot do its job as an acid since the environment is more acidic than the group. Like there's a lot of H plus ions here floating around. That's going to protonate that amino group and it stays protonated, which is a positive charge. The carboxyl group will have a negative charge at pH 8 because at a pH of 8, this carboxyl group pKa can now act as an acid, right? Since the pKa is lower than the pH, meaning that it's going to donate or release a proton, -1 charge. But we have to also be careful, keep in mind what charge is the protonated form of this carboxylic acid, which is neutral, 0, 0 minus 1, -1 charge, right? Because if we look at this last one here, which is tricky, a lot of people would have put -1 charge. Because at a pH of 14, we are going to deprotonate this amino group because the amino group pKa is lower than the pH. Right? When it releases a proton, people think of minus charge.
Right.
But it's not minus charge because we have to keep in mind the original, it's already positive as its protonated form. +1, -1, neutral, that's the answer. Yeah. Right.
So, I don't know if you have time or are willing to try to, but for, it was the quiz question of at what ranges of pH will the negative charges be present on each of the side chains of tyrosine, cysteine, glutamic acid and aspartic acid?
Right. So that's talking about, like that's one way cheating because that's experimentally determined, right?
Okay.
Because each amino acid, you know how we said pKa is the intrinsic property or characteristic of the group. These values were found experimentally. Like scientists were experimenting, like adding acid base until they found the isoelectric point, and then that's how they found the pKa. So that's why this was like a reading quiz because the reading gave those values, right? But more like application basis, like these types of questions
So
here.
I looked everywhere in the reading and I did not find it. Can you?
Oh shoot, yeah, I did read the reading. but it's experimentally determined. Wait, can I see the quiz question again? Just to make sure.
Yeah, it's this
Yeah.
one, the one via what ranges?
At what ranges of pH will the negative charges be present on each of the side chains? Oh, okay, this is application based right here. Actually, yeah. This is not the pKa. I thought I was asking for something else.
No, it's okay.
Okay, sorry. So
I just can we maybe go over one of these so I can,
yeah,
if you.
let's go over tyrosine. Tyrosine. Let's do it. And then, are there any other concepts that you guys are like?
The biggest one that had
If
me
you-
was the bicarbonate, and I think we've gone over that pretty well.
This is also a sneak peek of titration curves for next week when we go over deprotonating, protonating stuff. Yeah, sorry, I misinterpreted the question. Yeah. Okay. So this one, we have to actually know the pKa of tyrosine, R group, and like the other groups, amino group and the carboxyl group. Tyrosine pKa values. Okay. So I'm gonna draw out tyrosine. Its R group is going to be CH2 phenol. So tyrosine is ionizable, meaning that its side chain can get deprotonated. It can get ionized, forming an ion. Okay, so it will have three pKa values: one for the carboxyl group, one for the amino group, and one for the R group. The pKa for the carboxyl group is 2.20. The pKa for the amino group is 9.11. The pKa for the side chain is 10.07.
Use your 10 minutes.
Thank you.
Thank you.
So based on this, would this be considered an acidic or basic side chain? Like, don't look at the notes or anything, but based on the R chain, would you consider this an acidic or basic amino acid? Look at the pKa.
Basic.
Yes, basic, right? Because that's a high pKa. Right. So that's another way you can think about like how an amino acid is acidic or basic. The question was asking for.
And what ranges will the negative charge be present?
On each of the side chains of tyrosine. Right. So, what pH range would the side chain be negatively charged? So, its protonated form is neutral. Right? If you want to deprotonate this, how can we make this act as an acid and be able to delete its proton, be able to release a proton? At what pH? Higher or lower than the pKa?
Higher.
Higher. So the answer is going to be pH higher than. So if we want everything to be deprotonated, right? If we want like the whole amino acid to be deprotonated, it has to be higher by a magnitude of in the pKa logarithm in the pH scale 1, right?
Yeah, plus
So-
or minus 1 depending on what you want to do, right?
Right, plus or minus 1, depending on what you want to do. If you want everything to be negatively charged, right? Like let's say this R group here, like this. If you want everything to be negatively charged, then you want to be higher by 1, right?
So my answer's wrong.
Wait, what was the answer? Let's see.
Because I took the pKa value for it, I think I got that out of the book, and just
Uh-huh.
assumed that anything pKa or bigger.
Higher, yeah. So, and if you have a pH higher than the pKa, this would get deprotonated, right? But not 100% of it. Majority of it.
Anything.
Like let's say there's 100 of these. If you're at a pH of 10.51 or 10.47, like you said, then like 50 of them would get a negative charge. But if we want everything to be negatively charged, then it has to be +1 over.
A whole one over.
Whole 1 over, right? That's why I was like saying, is this question asking for like everything negatively charged? I just went with that. So just to be safe, I'm going to put everything negative charge, which is +1 over. If you want this to stay protonated, everything to be protonated, then what would that be? Like side chain charge of 0, which is the protonated form. If you want everything to be protonated, what would the pH range be?
Maybe like 1.2. If everything
Yeah.
you're saying.
Not the. Oh yeah, if everything, it would be 1.2, right?
Okay, yeah.
If you're talking about the carboxyl group, amino group, and the side chain,
Uh-huh.
then it would be 1.2, which is one below the carboxyl group, and everything would get protonated, right? But we're talking about the side chain.
Oh, just the side chain.
Just the side chain.
Neat.
So
It would be 9, right?
9.07, right? it's gonna be less than or equal to 9.07.
Oh, to neutral.
So at a pH of 9.7 or less, would this be protonated or deprotonated at a pH of 9.7 or less? Would this group be protonated or deprotonated? Right, so can this do its job as an acid? Like let's say we had a pH of 9.7. Can this group donate its proton? Can it release its proton? Or another way you can think about it is at a pH of 9.07 and this group has a pKa of 10.07, which one is the acid? The environment or the group?
The group.
Yeah, so think of pKa and pH as like if you have a lower number, it's more acidic.
Yeah.
More acidic, right? So at a pH of 9.07, it's lower than 10.07. And because it's lower than 10.07, the environment is more acidic.
More acidic.
Right. So the environment is going to protonate the group. So this is the protonated form of the group right here. Right? It's going to keep its proton. It can't donate that proton. It can't release that proton. Right? So this is going to stay protonated, which is neutral. Right? Yeah. Yeah. Any questions on this?
This is more conceptual and kind of still along the same lines, because it was the first question that said, list all 4 of the amino acids with side chains that will release hydrogen ions into the solution and hence have a negative electrostatic charge. How are we to have figured that out without having to go through all of the amino acid, or I guess not all of them, because not the non-ionizable ones,
Non-ionizable
but
ones,
the ionizable ones? How, without having to like work it out, what would we have? What was the key that we missed?
The key would be that if the side chain started off as neutral and is ionizable, then it would get a negative charge, right? What charge would the groups have if it's positively charged and it gets deprotonated, ionized? 0, neutral. That's how you could figure that out.
Oh my god. That's clearly I missed the concept.
It's okay.
Just edit my part out.